presentarles a Matthew Kahle de la Universidad Estatal de Ohio, Estados Unidos, en Columbus, y nos va a hablar de ciclos máximamente persistentes en complejos geométricos aleatorios. So that's the presentation as well. Thank you very much for coming.
Thanks very much for the opportunity to visit UNAM for the first time, and especially to give a talk here. And thanks for coming to my talk, everyone. So I want to talk about today some work that's in the intersection of algebraic topology and I would say geometric probability. And so that can be a little bit of a tricky topic because even people who are very trained, say in either topology or in probability, might not know the language of the other subject. So I'll do my best to keep things light and try to talk about the ideas and the big picture, but please feel free to interrupt and ask questions if you have them. So I want to talk about one paper today, and this is joint work with Omer Bobrowski and Primoz Škraba, and it is on the archive in more or less a final form, and it was just a couple weeks ago accepted to Annals of Applied Probability. Okay, so I want to start though, before I start talking about that paper, I want to overview a little bit why we might be interested in stochastic topology in the first place. Why should we be interested in this kind of interaction of probability and topology or geometry? So I think there are many reasons for that, and it's sort of a field that's been emerging over the last 10 years or so, but I still would like to take a few minutes to discuss some of those reasons. So one thing that I think we all believe in our hearts is that probability models nature in various ways. They say that you can't really even have a theory of quantum physics without probability, but even on kind of macroscopic levels, if I were to roll a 6-sided die on this table, and if I were to ask you to say what is going to happen when I roll that, one way that you would probably choose to talk about it is in terms of probability. You would say, well, we don't know which phase will come up, but we will quantify our uncertainty by saying the probability of any given side is roughly 1/6. So this kind of point of view comes up in physics in various guises, and I think that there are many needs in physics for stochastic topology. So one of the most classical that I'm aware of has to do with black holes. So John Wheeler, the astrophysicist, cosmologist, started suggesting as early as the 1960s that if we want to understand what is happening inside a black hole, we need a theory that is topological or geometric to account for relativity, the strong gravitational forces we can think of as curvature of space-time, and we should think of them that way, according to Einstein. But then Wheeler said, but we believe there's a singular point or a singularity inside the black hole, and if you are near enough that point, that you need stochastic kind of theory to understand things, that quantum kind of effects take over. And so the remarkable suggestion that Wheeler made was that the fabric of space-time itself inside a black hole is not any particular shape, it shouldn't be understood as any particular shape, but it should be understood as a probability distribution over all possible shapes. And he called it kind of quantum foam. So that's just one scenario in which you can, in physical reality, it's kind of at the limit of physical reality that we can even imagine, but where you can see kind of the interaction of probability and topology. But I would say there are probably many more, and something that I won't talk about today, but I think maybe the next 10 years we'll see a lot of interaction between stochastic topology and material science. For example, like many foams and grains of crystals, many materials that we actually encounter in nature every day, unlike black holes, which we only encounter really in our imaginations, or through a radio telescope or something. Many materials look like some kind of random cell complex, and understanding the topology and combinatorics of such random cell complexes, I think, will keep researchers busy for some time. Okay, so this is one point of view about randomness modeling nature. So here's another point of view, and one that I think is very relevant to the talk today. There's an emerging field of topological data analysis, or you could say topological methods in statistics. And this is a field that's being pioneered by many people around the world. And one of my postdoc mentors was Gunnar Carlson at Stanford. And another person who's prominent in this field is Robert Geist. And then this graphic I stole from the Israeli probabilist Robert Adler. So let me just say something about what topological data analysis basically does. You start with some kind of point cloud. You have some set of points, usually in some high dimensional space, although it could be in 2 or 3 dimensional space, and coming from just some data from some of your real world situation or from your physical experiments. And then typically what people do on that finite point set is they construct some kind of simplicial complex. So it's typically the Vietoris-Rips complex or the Czech complex, and then they look for holes in those space, and that's telling you something about the shape of the data. So the kind of flow, the pipeline is that you start with some set of points, a finite subset of Euclidean space, say, but you could use really any finite metric space, and then you run some kind of topological algorithms on it. So again, you typically build some kind of simplicial complex, and it's a little bit richer than that though. So to build a simplicial complex, you need to choose some scale, some choice of parameter. You're going to connect points if they're close, if they're nearby, but how close do you make that? So this has been a subject of a lot of study and research, and the feeling these days in topological data analysis, you could say it a couple of different ways. One way is that we don't know what the right scale is when we look at just some data set. They don't give us the data set and the parameter. We maybe have to find out the parameter. So that's one point of view. I would say a more refined point of view is that maybe there's even multi-scale structure. There's hierarchical structure intrinsic in some data sets. So there isn't only one proper scale to look at. You want to look at it on all scales. So rather than just look at a particular simplicial complex, there's actually like a filtered simplicial complex. So, and when your radius, your parameter is 0, then you just get a bunch of isolated points. And then when the radius is, say, infinite, or when it's very large, then you've made a very large high-dimensional simplex, and all the interesting topology has disappeared. But what people typically do is they look at so-called persistent homology, and persistent homology keeps track of how all the holes appear and how they disappear. So So this graphic of Robert Adler's that I really love is not exactly the situation that I'm talking about. It's somehow it's close philosophically, but it's a little bit different. So what we are actually looking at here is what's called a Gaussian random field. And this is the kind of thing Adler studies, and studies from a topological point of view. And this has been a subject of a lot of research over the last 20 or 30 years, by the way, and has been of a lot of interest in physics, that cosmologists look at one of these Gaussian random fields as a model for the early universe. And they can measure now that the early universe looks a lot, in some sense, like the density of energy in the early universe looks a lot like one of these Gaussian random fields. And then there are very small deviations from that are apparently of a lot of interest in cosmology, and some people say are responsible for the large-scale structure of the universe that we see today. So what this really is, he's got on this cube a random function that's kind of defined in terms of Gaussians, and then he's just taking sub-level sets of this function. So he's got but because of this random function and taking sub-level sets, you see some random subset of the cube, but then he's raising the bar and taking bigger and bigger sub-level sets. So this random little piece of the cube is growing. This subset of the cube includes that, and then this includes that, and it's growing. And so at this point the cube is empty, and at this point the cube is full. But then what we're looking at here is the persistent homology. So H0 keeps track of the number of connected components here. And so a new bar here is, the left side of a bar is when a new connected component appears. And the right bar is when two connected components merge together. So it's hard to see maybe that, if this were exact, maybe this dotted line here, there should be, about 8 or 9 bars. So, and then by the time you're at the end, there should just be 1 bar in H0, that last connected component. So then H1 is a little bit more involved. This has to do with kind of one-dimensional holes. If there's a sort of circle, say, somewhere embedded in your space that is not the boundary of any surface, then you get a class in H1. So here those classes are appearing, and then they're disappearing. And so persistent homology is really keeping track of all the topology, at least that you can measure with homology, and over all scales, over all parameters. So just the input is, typically in TDA it would be a point set, and then the output would be some kind of diagram like this. People draw these diagrams in different ways, by the way, and this is called a barcode. So every bar represents a homology class. It's a cycle that's being born and then dies. And what we'll see later in the talk, the other picture that people like to draw is a so-called persistence diagram. And for every one of those bars, we just draw 1 point. And it will be in this section of the plane, because the x-coordinate of the point is the birth of the cycle, and the y-coordinate is the death of the cycle. So if you project it down, this is when the cycle is born, and this is when it dies. And so that's the same amount of information as is in one of these bars. I actually sort of prefer so then you would get, instead of a picture of a bunch of bars, you would get a picture of a bunch of points in this octant of the plane. So again, that's the barcode, and this is the persistence diagram, but they're just 2 different ways of visually presenting the same information. Okay, so if this is the setup for topological data analysis, then we might like to know something about stochastic topology or probabilistic topology, because that would be the null hypothesis. If we just take some data and we run topological algorithms on it, and it spits out a picture like this, then, I mean, how do we know something interesting is happening? We might like to compare it with what is the expected picture, what is the expected persistence diagram or barcode for random points. What if your point set was just random? Then what kind of picture do you get? So that's the kind of story we want to talk about today. So finally, I want to mention that I think mathematicians, and not only physicists and statisticians, should be interested in stochastic topology. So for example, we might ask, what is a random manifold like, or what is a random group? And so what is a random group is something that I think it's fair to attribute to Gromov. At least, maybe he wasn't the first to study it, but he really pushed the whole field forward, or kind of invented the field as we know it. And Gromov suggested that, for example, that almost all groups are hyperbolic. And so what does that mean? Is it just someone is kind of saying their opinion is that, I've seen a lot of groups and most of them were hyperbolic. That's been my experience. Or is it actually like a well-posed mathematical idea? So it is actually a well-posed mathematical idea. So Gromov said, for example, we could take a given generating set and then fix that, and then add random relators. So the length of the relators typically go to infinity, and the number of relators also go to infinity at the same time. And there's a parameter that controls the relationship between the number of relators and their length, called the density. So if the density is 1, you're taking all the relators of that length, and if the density is 0, you don't take any relators, and you have a free group. So we can think of starting with a free group and then adding random relators. So we're taking kind of random quotients of this free group and seeing what we get. And the kind of remarkable theorem is that if the density is less than 1/2, then the probability is approaching 1 that you get a hyperbolic group. And on the other hand, if the density is greater than 1/2, then the probability is approaching 1 that you get a trivial group, which happens to also be hyperbolic by this definition of Gromov. So you kind of seem to get hyperbolic groups the whole way through. So there's some delicate things that happen right at density equals 1/2, and it's still an active study of research. But there's some kind of phase transition where your group collapses very quickly to a trivial group. You've added just enough relators where the whole group collapses. But before that, it's hyperbolic. And a lot of other things are known about such groups. For example, they are cohomological dimension 2. And there's a range in which they have Kazhdan's property T, if you know what that is. And deciding exactly what that threshold is probably the major open problem about density random groups of Gromovs. I think the latest is that it happens somewhere between density 5/24 and 1/3. And after that point, the group is property T. So this idea of modeling a typical mathematical object with probability is not unique to geometric group theory. One of Bill Thurston's last research interests in his life was random manifolds. And indeed, Nathan Dunfield and Bill Thurston introduced a very interesting model of random 3 manifold, and it continues to be studied. And one of the strongest results for such random 3 manifolds is due to Joseph Mayer, and he showed that a random 3 manifold is hyperbolic with high probability also. So this sort of parallels a little bit the story for groups, but the techniques are quite different in these two different settings. So I think these are, you hear people say, well, now that we know the geometrization conjecture is true for 3 manifolds, we sort of know that most manifolds are hyperbolic. But I think this is in a way a more precise statement to say it's a way of quantifying that most manifolds are hyperbolic. Dunfield and Thurston put a measure on them so that every manifold has a positive probability kind of for a sufficiently large parameter, and so they're sort of all in there, and then you can really like measure the property, typical properties of the three manifold. So we could say this about other kinds of mathematical objects too. For example, simplicial complexes or posets, and that's been the subject of a lot of study. What are random simplicial complexes like? What is their topology like? And that's a little bit what we'll talk about today, although we'll talk about a specific kind of simplicial complex that I think is maybe important for applications, especially to statistics. Okay, so that's just a little bit of background and motivation. Are there any questions or comments before we continue and get into the content a little bit? Okay, so we'll start with the kind of one-dimensional version. So this is a picture of a random geometric graph. I chose, or I had the computer choose, 1,000 random points in the unit square independently. And so that gives me the vertices, and then the edges are just, I'll connect them if they are close. And I chose some parameter. Maybe I'll say something about how I chose the parameter in a bit, and just connected them if they're close. So this is the typical picture of a random geometric graph. And they've been studied quite a lot. So the canonical reference here is Matthew Penrose's textbook called Random Geometric Graphs, and he works out many of the fundamental properties of such graphs in his monograph. So one thing that's nice about this setup, I should say right at the beginning, say compared to some other models of random graph, like the Erdős-Rényi model, is you really have kind of a lot of freedom. You can choose any underlying distribution you want. Say on Euclidean space, or if you want to work on a Riemannian manifold or in some more general metric spaces, sure, why not? I think probably all you need is a metric measure space. But Penrose concentrates most of his energy on and attention on Euclidean space, and the dimension is at least 2. You choose some kind of probability distribution, and he often assumes that for some of the nicest theorems that you have a bounded measurable density function. So you don't have like Dirac delta kind of functions with infinite density at some points. So, but just think like, say, a uniform distribution on a convex body, but it really doesn't need to be something like that. Like, what about a Gaussian or something? You don't have compact support. So what I'm saying is this model of random geometric graph is kind of, it's like an infinite dimensional parameter space. You choose your underlying distribution, and then you choose a random graph according to that. So once you choose your distribution, the usual thing to do is choose endpoints independently, and then connect them if they're close. So close is the kind of, the main parameter that you usually study is that radius r, where you connect 2 points if they're within distance r. So again, you just choose some distribution on RD. We'll always assume D is at least 2. And then N is the number of vertices. We'll choose endpoints exactly according, so this is independently and identically distributed. And then you connect them if they're within R, distance R. So we usually are interested in asymptotic properties as n goes to infinity. And so then we think of R as depending on n. So many properties we're interested in, if we want to find a sort of threshold where that property first appears, R is going to tend to 0 at some rate as n goes to infinity. And so we're interested, usually R is going to 0, but the interesting thing is at what rate does it go to 0? Okay, so here's a toy example, just a basic proposition. So let's consider this uniform distribution in unit square. I would say if r is much less than n to the minus 3/4, then we should expect that there are no triangles with high probability. So with high probability here, it might have been on the previous slide, but throughout the talk it always means with probability going to 1 as n goes to infinity. So the other terminology people use that's slightly more descriptive is asymptotically, almost surely. Almost surely means probability 1. Here we have not one probability space, but a sequence of probability spaces going out to infinity. So we say asymptotically, almost surely. But I'll just say with high probability is going to 1, you don't get any triangles, and that's sort of the right answer. If r is much larger than n to the minus 3/4, then you get lots of triangles. So I'm being a little bit vague here with this much less than, much greater than. So what do I mean? I'll just say here, if r over n to the minus 3/4 tends to 0, and here if r over n to the minus 3/4 tends to infinity. Okay? And we could say more. If r over n to the minus 3/4 tends to a constant, then the expected number of triangles is going to some constant. And in fact, the limiting distribution of the number of triangles is what's called a Poisson distribution. So you can say lots of things. This is a pretty coarse statement. And maybe we're interested in more general subgraphs than just triangles. But like I said, this is just a toy example. So but I think you will get a flavor already. We'll just sketch a quick proof of this proposition, because like where did that exponent minus 3/4 come from? What does that have to do with triangles? So here's a sketch of a proof. Let's just look at the expected number of triangles. So by linearity of expectation, it's n choose 3 times the probability that given 3 points form a triangle. And the thing is, so those 3 points form a triangle in the graph if x is adjacent to y, y is adjacent to z, and z is adjacent to x. That's what that notation means. And unfortunately, those are not independent events, or else we could compute the probability for one of them and just cube it. So that's the bad news. But the good news is some of them are independent. So we break it into these 3 events, and probability that x is adjacent to y and probability that y is adjacent to z turn out to be independent events. So x being close to y has nothing to do with z being close to y. That's plausible, right? So you can check that. So we have this third term, probability that z is adjacent to x, conditioned on x is adjacent to y and y is adjacent to z. So what we have here, we're conditioning on x and z both being close to y. So close to y means we've got a disk of radius r centered at y, and then both x and z are in that disk, right? So we've conditioned that both these points are inside this disk. Now what's the probability that they are themselves within one radius? So I'm just claiming that it's positive. It's bounded away from 0. I could even say something funny like take this little region here. The probability that x is in that region is positive. It's the area of that region divided by the area of this disk, right? And the probability that z is in there is conditioned that it's in this disk is also positive. The probability that they're both in there is just that probability squared. So there's some constant that represents this probability. It's some constant between 0 and 1. So let's forget kind of constant factors and just try to get the rough rate of growth of this function. So n choose 3 is roughly n cubed over 6 as n grows large, right? So I'm just going to forget the 1/6 and call this n cubed. So this notation means proportional to, that this is the right answer up to a constant factor. Now what's the probability that x is adjacent to y? Well, it's just, you know, the area of this disk, which is pi r squared, divided by the area of the square, but it's the unit square, so that's 1. So the probability that x is adjacent to y is just pi r squared, conditioned on wherever y is, and x just has to be in that disk. And then similarly, probability that y is adjacent to z independently is another pi r squared. And then, so I've got, you know, n cubed over 6 times pi r squared times this constant c, which was the probability that x is adjacent to z. So if I ignore all these factors of pi's and 6's and this c, I get something that's like n cubed r to the 4th. Those are the interesting parts. N is going to infinity and r is going to 0. So this is where it comes from. If r is much greater than n to the minus 3/4, then the expected number of triangles is very large. And if r is much less than n to the minus 3/4, then the expected number of triangles is going to 0. Okay, so that's just a sketch of the proof, but just this kind of reasoning gets you pretty far in random geometric graphs. So the thing that, yeah, so maybe I'll just leave that example there. So here's a more interesting theorem, and I'm actually not even sure quite who to attribute this to. It's sometimes called the Gilbert disk model, because this was like early version of percolation theory in the 1950s, or certainly by the 1960s. Matthew Penrose writes down some precise results in his book that are kind of in this direction. So the statement here is that there's some phase transition where a giant component is born. Very quickly, the giant component is born. So there's some constant over square root of n. So notice now the power of n is not minus 3/4, it's minus 1/2. And this is where kind of all the action is. This is what people sometimes call the thermodynamic limit, or the critical regime. And it's really for this reason. So there's some special constant c star, which is known, as far as I know, to physicists, but not known to mathematicians. And what I mean is, you can determine it experimentally, but no one knows a mathematical reason why it is what it is. So if you're less than that constant over square root of n, then all your connected components are only logarithmic in size. And on the other hand, if you're a little bit bigger than that constant over square root of n, then all of a sudden, there's a unique giant component that has a constant fraction. So big omega of n here means it's a lower bound, just like big O is an upper bound. So there's some constant times n, which depends on this constant, but not on n, so that you actually get that fraction of the vertices in your giant component. So you go very quickly from logarithmically many vertices in your largest component to linearly many vertices. And that's called the percolation threshold. So this is a non-trivial theorem. And actually, this direction is kind of easier because it's a little bit more of a local story, and it's not so different than this kind of reasoning that we did over here. I would say, though, this has a lot more content to it. It's a more of a global picture, and you need to show that you really get a lot of components in that giant component. And we're not asserting here that in this proposition as it's written on this slide that giant component is unique, but it is. There's only one giant component on a constant fraction of vertices, and then the second largest component still only has logarithmic many vertices. So these are kind of deep statements in percolation theory, and we'll actually use this fact at some point in the talk, at least the easy direction of it. Okay, so that's just a sort of introduction to random geometric graphs. I said that was the one-dimensional version, which might have been confusing because we're in a square or in the plane. It seems two-dimensional, but I mean the graph itself is one-dimensional. There's only vertices and edges, and that's in contrast to what we're going to talk about now. So random geometric simplicial complexes. So again, 1,000 points in the plane we connect them if they're close by an edge. And then if you have 3 edges that are all connected to each other, 3 vertices that are all connected to each other by edges, then we'll fill that in with a 2-dimensional cell. So there's actually a 2-dimensional part here. And this is called the Viatorus-Ritz construction. And so it's a sort of higher dimensional analog of the random geometric graph. And people have been studying these for the past several years and studying what are their expected topological properties. And one kind of thing you could study is, like, for example, when does homology appear and when does homology disappear? And then maybe in the non-trivial range of parameter, you could ask how large is homology, what are the Betty numbers, and so on. So what do I mean when I say when does homology appear? In this case, I mean when do cycles start to form? So first of all, cycles start to form, but and so there's some non-trivial homology in degree 1 and H1. But then if you increase R here, then you're going to get more and more edges. So it seems like more and more cycles, which is true, but more and more boundaries too, because those cycles are going to get filled in. You're going to get lots and lots of triangles. Let's take it to an extreme where R is infinity. Then every pair of vertices is connected by an edge, and every triple, it's got a filled in triangle. So at that point, you have no homology. Everything is filled in. So it's a little bit surprising here that if you look at homology, like H1, there's actually 2 phase transitions. There's one where it first appears, and then one later where it disappears. Okay. So I mentioned one possibility, the Viatorus-Ritz construction. The check construction is similar, but maybe I'll skip the details for now. Okay, so here's the kind of theorem that people have proved in this area. That in the -3/4 that we talked about before, there's no homology if R is less than in the -3/4 with high probability. On the other hand, I'm sorry, this is a typo. This should be log n over n to the 1/2 power. So it's roughly n to the -1/2, but you need this little logarithmic factor. So R much greater than log n over n to the 1/2 implies H1 equals 0 with high probability. But these are both, in some sense, the right answer. If R is in between those extremes, then, and again, there's a 1/2 power here, then you do get some homology. So these describe the 2 phase transitions. Homology is born at that point, and homology dies at that point. And you can do, say, you could have an analogous statement where you're in, say, d-dimensional space, and you're looking for cycles in degree I homology, and you'll see similar behavior where homology is born and where homology vanishes. So some places where you can read about this, I have a paper that kind of works out these phase transitions in discrete and computational geometry. And then Omer Bobrowski and I wrote a survey article. So already, in the last 5 years or so, a lot of people have written papers about the topology of such kinds of random geometrics and partial complexes. So this survey kind of tries to overview this. By the way, you can think of these statements as a little bit, that where they started is actually Penrose and others worked out when does the random geometric graph become connected. So that's a story to topologists, that's a story about H0. Okay, so, but the thing is, you just start with n isolated vertices, and you increase R and things become connected. But everything is behaving in a monotone way. You're only killing H cycles in degree 0 as you make your edges longer. But here, so there's only one phase transition for connectivity. But here for higher homology, there's 2. Okay, so these are the kinds of things that have been known. So here's a picture of a persistence diagram for random points. So I guess you could talk about, when is homology born as what is the smallest x-coordinate of one of these points, and when does homology die as the highest y-coordinate of any of these points. But for applications to topological data analysis, maybe we would actually like to understand this whole picture. Maybe we would like to understand everything about it and predict it. But so far that people have been thinking about it, but that seems a little bit out of reach. So technically I would say you can take this probability distribution in IID points, some probability distribution on RD, that gives you a random filtered simplicial complex, and you can push forward that measure to get a random point process in this kind of octant of the plane. And we'd like to know things about that point process. In particular, we would like to know how persistent are the maximally persistent cycles, and the reason is that in many applications in TDA, people kind of pretend like the long bars and the barcode are kind of represent signal, and the short bars represent noise. And so they just threshold at some point, and I'm not exaggerating to say they just eyeball it. They look at their picture and they say, well, I think we'll just say these things are signal and these things are noise. So this motivates what we're interested in. We'd like to understand this whole point process, but we don't know how to do that yet. So we're just going to look at one particular variable, which is the maximally persistent cycle. So let me give you a couple definitions. So given a cycle in persistent homology, B is its birth radius in the Viator scripts or check filtration, and then D is its death radius. And then we're going to define P, the persistence of the cycle, to be death radius divided by birth radius. So that's our measure. And I feel like I need to justify this, and when I give talks at conferences, at TDA meetings, I feel like I have to have the following slide to justify this, because people are often interested in death minus birth, which is just kind of, I guess, the length of the bar and the barcode. And I'm just saying, let's do things on log scale. I mean, if you take log of P, that's log death minus log birth. But I feel like I need to justify that. So here are some justifications for this multiplicative definition. So if we're doing this problem in geometric probability, the initial point set is random, and we build these random geometric graphs, and on top of them random geometric spatial complexes, there are many, many cycles where the death radius of the cycle minus the birth of the cycle is just approximately the death cycle. So these are all going to zero as n goes to infinity, but what I'm saying is this is going to zero much, much faster than this. So if you just look at death minus birth, you're really only, if you only look at the first order asymptotics, then you've lost all your information about when the cycle is born. So somehow it's actually an easier problem in geometric probability, and I feel strongly that it's a less interesting one. But just taking a step back, I think actually this is, for many applications, the way we should measure persistence, because in many scientific applications, we want dimensionless parameters. We want things that are scale-free also. So, okay, and then, yes?
How do you keep track of the cycle?
Right, so this is a big story, and it's not clear that it's well defined to have death and birth radius of a given cycle, because cycles are only defined up to boundary or something like that, right? So it turns out there is a way to keep track of these things, though, in persistent homology. And unfortunately, it's slightly technical, and so like the easiest, some people talk about it these days in terms of fancy, like they like to talk about quiver representations and things, but I feel like the most down-to-earth way, the way I learned it, was that you think, I'll just say one thing, you have, you're doing, first of all, homology over a field coefficients. So K is your field. And then you think of T as your time or your radius or whatever. It's your parameter that's varying. And then homology ends up being a KT module. And so the thing is, because K is a field, the polynomial ring over a field is it's a finally generated module over a PID. So we can use the classification theorem for such modules. It's just like finally generated abelian groups, where you just break it up into 3-part and torsion part, and those things end up being the bars in your barcode. It tells you uniquely when things are born and when they're defined. So it's a purely algebraic thing, and people have done a lot of work. There's a whole field now of computational topology, people computing these things very quickly. So you can compute, let's say you're given a finite metric space, you can compute persistent homology, the whole barcode, and matrix multiplication time. So it's not just polynomial time, it's very, very fast. Okay, so also I want to say something that's a little bit technical, but I know there are a few people here who know what the check and Viatorus-Rips constructions are, and that they're both important in this theory. So the check construction is essentially just to take the union of balls of radius r. And the thing that's good about the check construction is that it's homotopy equivalent to whatever, it's a simplicial complex, the nerve of that cover, and it's homotopy equivalent to whatever it covers. So the check complex is really good topologically. It's sort of topologically accurate, and it captures whatever you want it to. On the other hand, the Viatorus-Rips construction is much easier to compute, because just once you know the one-dimensional skeleton, once you know where all the vertices and edges are, you know everything. You just fill in all the higher dimensional cells that you can. And so the Rips construction takes less memory in a computer, and is faster for many kinds of computations. So they're both important in the theory, and sometimes you'll see people in papers or in talks just say, well, you know, we have these maps between them, so it's kind of all good, and we can just go back and forth between homology between them. And that's sort of really irritating, I think, to topologists to just say it's all good. There really is actually a relation here. So there's maps between the check complex that includes in the Rips complex, which includes in the check complex with twice the radius. And so you can't compute the homology of one of these just from looking at homology of the others. But because you have these maps going back and forth between them, I mean, this continues, right? Now we can include that in the Rips complex with radius 2r, and so on. So you have maps back and forth between check and Rips complexes. So that's actually really good news for persistent homology. That if you know a lot about the persistent homology for the check complex, you can compute at least a lot of things about the persistent homology for the Rips complex and back and forth. But I just want to point out that that's a multiplicative relation. And this constant 2 here, this works for any metric space, just by the triangle inequality. But if you're in Euclidean space, you get a slightly better constant than 2, but the relation is still multiplicative. So, okay, so with that in mind, our results hold for either the Rips or the check filtration. If you prove it for one, that fact on the last slide gives it to you immediately for the other. So let me state our result. So, so we choose endpoints, say uniformly in unit square, and then we want to find the maximally persistent cycle. And I'm saying it's of order log n over log n. And what I mean with this big theta notation is that there exist constants C1 and C2 that do not depend on n. And so that with high probability, the maximal persistence is between this constant, you know, times log n over log n times that constant times log n over log n. So that's our statement. So this is, in a way, I think, to me, this is good news. This is actually saying that these cycles don't persist for very long. They kind of wink in and out of existence very quickly. So let's try to get a feeling for this. On an earlier slide, I showed that we understand, and it's been known for maybe 5 or 10 years, when homology first appears and when it disappears. And so where it first appears was n to the minus 3/4, at least for the Ricks complex, and where it disappears, there was a log factor, but about n to minus 1/2. So if you just take, so there's nothing before that first cycle appears, and there's nothing after that last one disappears, but if you take the ratio of those, you get like n to the 1/4. So it's a power of n. So it seems like you could get some cycles that persist for quite a long time. It could be a power of n. But this theorem is saying they do not persist that long, that it's only like log n, and it's even smaller than log n. It's log n over log n. So this is something we worked on and off for a few years, and we kept trying different things, and eventually, so we were trying some techniques for lower bounds and some techniques for upper bounds, and then we were surprised and delighted when we got them to match up to a constant factor. It was just kind of one day things snapped into place. So here's a picture of actually taking the maximally persistent cycle on one axis. What is the persistence? Death over birth. And then on this axis, we compare it with that function, log n over log n. And 5 doesn't seem very big, but remember, that's not n. That's log n over log n. So n here is about 1 million. There's about 1 million points. And then there's a lot of cycles, and you take the maximal persistence over all of those. Okay, and if you plot this and just do a scatter plot, so we run this experiment many times for various values of n. This line here is the best fit line, and it seems like they're kind of lying along that line. Okay. So the upper bound ends up being much more interesting than the lower bound, and it's where most of our work is. In the remaining kind of few minutes, I just want to say a few words about what it's like. The lower bound is really, it's something like this. We want to get, we actually try to create a cycle that's got a large persistence. And so you can imagine we divide the square up into a really fine grid, and you have a lot of parameters to tune, and you need to make the sizes of these squares just right. But then you make the sizes of those squares just right, and you can find somewhere in this big square, you can find a bunch of squares so that there's at least one point in each of these squares, and then some cube inside or some square inside where there's no points, and that these squares are small enough and close enough that anything in this square is connected to anything in this square. So we get some kind of cycle, and there's a cycle, we've got a lower bound on when it's born and an upper bound on when it dies because it's empty, there's nothing inside it. So you just have to sort of like cook up a cycle, and it's there, but what's hard is to show that there's no no cycles that persist longer than that. Or at least it was hard for us. It took us a long time to figure out. So this was a breakthrough idea. We decided we were a little bit inspired by percolation theory, and we said, well, what if you set our star, this critical threshold, to be some constant over square root of n for some small constant? Then we're going to divide the cycles into two categories: cycles that are born before that point, and cycles that are born after that point. So we'll call the ones before that point early born cycles, and cycles born after that late born. And remember, all the cycles are bound by log n over square root of n. And so if you take the ratio of that with that, we've already got square root of log n, which is less than this, log n over log n that we're going for. So all the late born cycles are fine. We have an upper bound on their persistence. So what we need to handle is the early born cycles that are born before this. And we're going to choose C sufficiently small so that they can't have, so what we know about R being like constant over square root of n for small constant is that all the components are only logarithmic in size, right? But if you're on it, so they're born on a small connected component, that's actually already enough to rule out it persisting for a long time. It's just, it's small, it can't, so we have to argue that, but that's our inspiration. So if it's, so we have to handle the early born cycles. So we say because R is small enough, that there's a bound on the number of connected vertices in a connected component, which is only logarithmic. And then we have how many vertices are in there, and we have their length, is essentially R. So then we have something about the length of the whole cycle. And then we have, we can control from the length something called the filling radius. Let me show you a picture. So here's a cycle in the plane. The filling radius is how much I need to thicken that cycle before the homology is killed. So this is, an idea that, well, I'll say something about where this idea comes from. So then that cycle is a boundary, and so homology is trivial. So in this case of H1 in the plane, the maximal filling radius is proportional to the length. There's some constant factor that relates bounds on these. And then finally, you relate the filling radius back to persistence. Essentially, once you pass the filling radius, then you've killed the cycle. So, okay, so what this gives us when we compute all these things is that the early born cycles have persistence at most big O log n. So remember, we had the late born cycles were big O square root of log n, and now we have the early born cycles are big O log n. And that's almost what we wanted, except we wanted something a little bit smaller than this. We wanted log n over log n. Okay? But we had a little room to play on the late born cycle side. We have that because we have that square root of log n, and we, so that's a lot smaller than what we're going for. So so this is almost the right proof. Now, so remember what we started with this proof was we set that threshold radius between early born and late born cycles to be a constant over square root of n. But then the breakthrough that eventually, once we had all the other pieces in place, was to play around with the parameter and it sets that R star to be a little bit smaller, some small power of log n over square root of n. So alpha here needs to be less than a half or less than a quarter or something, but just sufficiently small alpha. And then we just go through the whole argument again. And now it turns out the early born cycles are born on a connected component that's not just logarithmic in size, but it's a little bit smaller because R star is smaller, and you get down to log n over log n. And this essentially matches what we got with our lower bound, proving that some cycles with certain geometric properties exist. So now let me just state the general form of this. So we do a d-dimensional cube, say, and they don't really have to be uniform distribution. Everything that we say would hold if you had, say, and it doesn't have to be a cube. Let's say you have a Riemannian manifold with boundary, or a convex body in Euclidean space if you want, and you just have a probability distribution that's bounded above and below. It doesn't have to be uniform. Then you're going to get something that's like this, of the same order. But in our paper, to keep things simple, we only do it for the cube. So if you're in a d-dimensional setting, then you better look at degree I homology, and I can be anywhere from 1 to d minus 1. And this is the theorem we get, that the maximal persistence is of order log n over log n to the 1 over I. So again, this is just saying this is the right function up to a constant factor. And there's a lot of things this depends on. It depends on I, the degree of homology you're in. Also, it depends on d, the ambient dimension. And finally, it depends on whether you're looking at the check or Rips filtration. But one thing I really like about this work is that the result holds for both check and Viatorius Rips filtrations, and that the answers could only be different up to a constant factor. But that's not a deep fact, it just comes immediately from these inclusion maps that you have that are multiplicative. So, but I think it's a nice fact. So this is what we get. And the proof is very similar to what I just showed you, except, so here's a couple experiments, more experiments that Primo Schrabe implemented. So computing higher homology, we weren't able to do it with 1,000,000 points. So maybe this is more like 1,000 or 10,000 points. But again, if you plot log n over log n to the right exponent versus the maximal persistence, things seem to lie along the line. And we would actually guess that there's a strong law of large numbers here, that if you divide the maximal persistence over this function as n goes to infinity, that it's actually approaching a constant. So we just showed that it's bounded between two constants, but probably the truth is it's approaching some constant. So that would be one of the next things to do. And here's a picture in 4 dimensions. The variance looks like it's bigger, things are spread out, but again, I would expect that as it goes to infinity, things are right along this line. So I just want to tell you the last ingredient. The proof on the upper bound is very much the same as what we said before, but this is the trickiest part, to go from the volume of the cycle to its filling radius, and that's an isoperimetric inequality is what we need. And this is the theorem that we use. It's Federer and Fleming from 1960. They have a beautiful Annals of Math paper. And what they're interested in is you have a k-dimensional cycle, just a singular cycle in d-dimensional Euclidean space. Because you're in Euclidean space, there's no homology. So it's a cycle, it's definitely the boundary of something. So relate the k plus 1 dimensional volume that it bounds, the smallest thing it bounds, to the k-dimensional volume of the cycle that you start out with. And this is a really important paper. It appeared in Annals of Math, but that kind of undersells it, that this is in some ways the beginning of the whole field of geometric measure theory as we know it today. There's some tricky things here in their paper, and it's a hard paper to read, at least for me, because you need to know what do you mean in particular by k-dimensional volume and k plus 1 dimensional volume of the cycle on the boundary for singular cycles. So they restrict their attention to Lipschitz singular cycles, and that makes things a little bit better. But for us, we're actually going to just have a simplicial complex that's embedded in Euclidean space, so we don't have all these measure theoretic subtleties, and we just get to use their theorem as a black box. So the formulation we use is, rather than relating the volume of the k cycle to the volume of its whatever it bounds, the k plus 1 dimensional thing it bounds, that chain, we just use this filling radius formulation, which is their main tool. So I cannot recommend highly enough Larry Goose expository notes. So he's actually talking about systolic geometry and Gromov's systolic estimate in here. But what Gromov was inspired by was Federer and Fleming's original argument. And Goose just makes it crystal clear how to prove this in just 1 or 2 pages, where I find the original paper of Federer and Fleming quite technical. So anyway, this is what you get. The filling radius is like the power 1 over k, which is just what you want for a k cycle. So that's our kind of the isoperimetric inequality that we use to get an upper bound on persistence of cycles. And then everything else is kind of standard geometric probability kind of tricks that you use in random geometric graphs, and a little bit of topology and combinatorics to relate this back to the persistence of the cycle. So I think I'll stop there, and thank you for your time and attention.
¿Alguien tiene una pregunta?
Typically in the random graph setting, if you have like monotone properties, you expect 1 threshold. I was wondering what replaces monotonicity to get 2 and not say 3 or 4.
No, it's a really great question. And I don't really know the answer. It's something I've been wondering for maybe 10 years or so. Since I first started seeing in these random simplicial complexes that often, let's say in a random Rips complex or something, there's 2 thresholds, one where homology appears and one where it disappears. So what allows us to end up proving something like that, we usually take advantage of some other properties that are monotone, and sometimes there's 2 monotone properties, and if and the intersection of them is enough to prove there's, say, some non-trivial homology, or one of them is enough to prove there's no homology, the other one is also enough to prove there's no homology, or the negation of one of them. So you get the intersection of 2 monotone properties, and then between, so then and they overlap in some interval, and so you see some non-trivial and so you get the two phase transitions just from the intersecting these two monotone properties. But that doesn't really explain it. I feel like that's just the kind of technique that we use, and we try to get a handle on something that's intrinsically non-monotone by using monotone things that are easier to understand. And so that's the structure of the proof. We show there's some non-trivial homology by showing this holds and this holds, and both those things are monotone, easier to handle. But it doesn't turn out that non-trivial homology is actually equivalent to the intersection of those two properties. It's just sufficient. So I didn't really know, and when I first started getting into this as a graduate student, I started trying to do literature searches for non-monotone properties in random graphs, and I just couldn't find much. And there's so much of the theory is really built for monotone properties. So like one of my favorite things is to think about is like sharpness of thresholds. There's some really wonderful work by Friedgut and Kahle and others that says for any monotone graph property, the threshold between probability 0 and 1 happens in a very narrow interval, and sometimes it's even narrower, but there's an upper bound on how wide the interval between 0 and 1 can be. But we also find like similar kind of width intervals or even shorter ones in these situations where homology vanishes, just like you would expect it to do for a monotone property. So I asked Gil Kahle and some other people, well, could we generalize Friedgut's work to on sharp thresholds for monotone properties to non-monotone settings? And Gil Kahle said he thinks that would be really interesting and would have a lot of applications in percolation theory, but so far I don't think anybody has done that. So somehow I find that the fact that these are non-monotone properties one of the most interesting and surprising features of the whole subject, but I don't know if anybody has studied that just for its own sake yet.
So the Federer-Fleming result, I think that holds for metric measure spaces, right? There's some generalizations for that. And you were saying that your main theorem actually also holds for Riemannian manifolds.
I suspect that it does.
So maybe, so potentially you could push this all the way to like metric measure spaces.
I think potentially. I mean, so you may already know more about the Federer-Fleming paper than I do. I thought things were in living in Euclidean space and Lipschitz cycles, but you think that
for that, I mean, their result, but I think it's been expanded because these metric measure spaces have been pretty popular in Riemannian geometry over the
So yeah, that would be very interesting. Well, another situation, even if what I'm saying is true, let's say you have a Riemannian manifold, possibly with boundary, and you just have a density function bounded above and below. I bet this still holds. But another situation that's very natural, I think people are thinking about it, but I don't think anybody has written it down yet. What about like a Gaussian distribution on Euclidean space? How persistent are maximally persistent cycles then? It seems like another really natural example to look at. And my guess is it's the same order. They're like log n over log n to the 1 over I, where I is the degree in homology. And I guess the feeling I have is that if you look at these, if you take a bunch of points in a Gaussian distribution and take the little disks of radius r, once r is kind of in an interesting regime of parameter, then those disks kind of cover, you have like a core that's completely covered, and so it almost looks like a uniform distribution on a disk, or a density that's bounded above and below. And then you have some free floating things out here. But then I think the maximally persistent cycles are going to be born and die inside here, and so you're going to be back to this situation where you're on a Riemannian manifold with boundary, and your density is bounded above and below. So my guess is that this rate of growth of log n over log n to the 1 over I power is just a law of iterated logarithms that is a kind of a universal fact, and then I bet it would be really cool if it's even true in that level of generality for some kind of metric measure spaces with nice enough properties that you see this as, you know, how persistent cycles are. That would be my guess.
Si nadie más tiene alguna pregunta, le agradecemos. Muchas gracias. Y en 2 semanas viene Andrés Pedrosa de la Universidad.